Hi ladies and gentlemen, welcome to Lesson 4. This is section 1.4. It's a little bit longer section today, so I'll try to keep it to the standard 20 minutes-ish for the video, but it might take a little bit longer. Let's jump right in. Starting here, we're going to talk about, as we do all the time, the introduction to this section. First of all, let me just make one note that we discussed previously, which is this term length. So length is oftentimes used in Strang to mean magnitude of a vector, which is the actual physical length of the vector. So we like to think of length as magnitude. Magnitude is a better term because we can't really confuse it with anything else. In this case, he's talking about length of a vector as the number of components. So he's thinking about something that looks like this as length equal to 3. So that's okay. It can be a little bit confusing. We will try to use the word magnitude for the magnitude of the vector. So the magnitude of this vector would be the square root of 1 plus 4 plus 1, which is equal to square root of 6. And that's going to be magnitude. And we'll try to keep that straight, and we'll use the term length for the actual number of components inside of a vector. All right, so that's one thing. The second thing here, he notes that if we take the dot product between a row of A and a column of B, that's how we calculate when we're doing multiplication. And we always are going to think about the rows on the left, columns on the right. Anytime we do a multiplication, A times B, it's going to be a dot product of the rows of the A matrix and the columns of the B matrix. And because that we are building matrix multiplication as a bunch of dot products, which is one way to think about it, and he talks about the linear combination of the columns of A, which of course is an important idea and is really kind of the stronger conceptual piece of how we think of matrix multiplication. But because of this, we have one really important rule for matrix multiplication. Think for a minute that A is size m by n, m rows and n columns. And then think that the size of B is P by Q, where P is the number of rows in B and Q is the number of columns. Because we're taking these dot products, then we need the number of entries in every row of A, which is the number of columns of A, and the number of entries in a column of B, which is the number of rows of B. We need those to be equal so that we can do a dot product. We have to have the same length vectors there. And what that means is, for us to do matrix multiplication, n has to be equal to P. That's a requirement. It's called the inner dimensions. The inside dimensions have to be equal to one another in order for us to be able to do matrix multiplication. Then the resulting size of the matrix, right? So this is necessary. And then the size of AB is going to be m by q. So the outer dimensions here give me the size of what the resulting matrix is going to look like. And what that means is, if we have, for example, a 2 by 4, and we're going to do this as a specific example, I have a 2 by 4, 2 rows and 4 columns by 4 by 2, 4 rows and 2 columns. This is matrix A and this is matrix B. We can do the multiplication because the 4s are equal to each other. And then the result will be 2 by 2. Okay. That's just an idea that we need to keep straight for ourselves. Also then, he talks about columns of A, which are multiplied times B, produce the columns of A, B, and he shows that right down here. And that's easy to understand. I'm going to leave you to read that, but there's one really somewhat subtle and important idea that comes from this. This thing here is a vector. Every time I take a matrix A and multiply it times a vector, that product is a vector. And it follows the exact same idea that we just discussed. So if A is 3 by 3, and we multiply by the vector x, which is 3 by 1, then the result is a 3 by 1 vector which is A times X. So you just need to become accustomed to seeing that a matrix multiplied times a vector is a vector. It's another vector. That's all. And you can think about that as the linear combinations of the columns of A. I'm taking the columns of A and I am linearly combining them by using the matrix or the vector X. All right, the item number 4 has to do with commutativity and associativity and distributivity. I'm going to let you read about that. That's in the section. And then also we have the C times R decomposition. So there's a somewhat similar term here. We call these things matrix decomposition or matrix factorization. Both terms are used. So in this section, we're going to start with our very first one, which is taking A and writing it as a matrix product of C times R, where C contains the linearly independent columns of A, and R tells us how to use those linearly independent columns to build the matrix A. And we'll talk more about that in a minute. Okay, go ahead, look through. This is very similar to what Strang has talked about previously with thinking about multiplication as rows, the dot products of the rows of A and the columns of B, but then also thinking about matrix multiplication as linear combinations of the columns of A. So what I want to do is I want to provide you with a visual that has been very helpful to me ever since I first learned it back in the late 1990s when I was in graduate school. I think it is the best way to think about matrix multiplication because it ties together both of the ideas of the dot products and the linear combinations of the columns. So for this first problem, I want to take a look at the matrix multiplication of, for example, A times B. So we're going to take matrix multiplication. We know that this is 3 by 3 and this one is 3 by 3. The inner dimensions match and the resulting matrix is going to be the outer dimensions, which is going to be a 3 by 3 matrix. Now, here's the idea. I want you to think about grabbing the first column of B and using that column to build the first column of the product AB. So we're going to build this product AB, and the column over here corresponds to the column here. And what we're going to do is we're going to rotate this, and we're going to sweep it through these rows of A. So we could just do the dot products, and that's really what we're going to do. But this is a visual that helps us easily see what's happening. What we're really doing to build the first column of AB here is we're taking one copy of the first column of A and we are subtracting a copy of the second column of A. That's this idea of sweeping through here. So we have 1 times the first column and -1 times the second column. And what that allows us to do is very quickly then say, well, I'm going to take the first column and I'm going to subtract the second column, which is going to be -2, -4, -1. I could calculate all the dot products and I would find that the 3 dot products give me those values. This is just a kind of an easier way to think about it, and it's broadly applicable. Again, pulling together the idea of the dot products and the columns of A and the linear combinations of the columns of A. Let me flip this one back. And I'll put it back. Whoop! I've got it flipped the wrong way, so I'm going to flip it twice here. All right. So for the next one, I'm not even going to bother flipping it. If I do the same thing with this column vector, and I flip it over and I run it through the rows of A, what am I going to end up with? Well, I'm just going to end up with a copy of the first column here. That's it. So I know immediately this is 2, 4, 1. That's what I'm getting with this flipped over and swept through the rows of A. Let me do one more here. I'm going to take this and put it to the left and think about sweeping it through. So I'm going to take 0 copies of the first column of A, 1 copy of the second column, and 2 copies of the third column. So I have 1 copy of the second column and 2 copies of the third column. That's going to be a 12. This is going to be a 24. And this is going to be a 12. Right? Again, if you did the dot products, you would end up with the same thing. It's just a different way of thinking about it that helps us to be able to do this a little more quickly and to better understand what the ideas are associated with what Strang refers to as the row way and the column way of doing matrix multiplication. Let's do another example here. Again, in this case, we have what? We have a 2 by 4 matrix, 2 rows and 4 columns. Here we have a 4 by 2 matrix. We see that the insides match and the resulting matrix is going to be 2 by 2. And now we can grab this column and we can flip it. And we can sweep it through and we can see what we're going to end up with. We're going to end up with 1 copy of the first column, no copies of the second column, 2 copies of the third, and 4 copies of this last column of A. Right? So again, doing the dot products really, right, I'm going to end up with a 3 minus 2, which is just a 1. And then for the second row, I'm going to end up with a 1 and a negative 1 and a 20, which is going to give me 19. Okay. So it's just a way in which I can think about doing this. And actually, I've got it wrong, right? I've got a negative 2 times a negative 1, which is a positive 2. So it's 1 plus 2 plus 20, which is going to give me 23. Let me just make that adjustment here. So this is going to be 23. And then I'll put this one back. And for the second column, I'm not even going to flip this one. Just think about it. We flip that over and we're going to end up with a negative 1 copy of the second column. So we're going to end up with a negative 1 of this and 1 of this. Negative 1 plus 1. So a negative 1 here is going to give me negative 2. Adding 1 is negative 1. And then here I end up with just a 1. So that's just a negative 1. So this is my product for A times B. One more example. I'm not going to rotate on this one. I just want to do this one to show you the size of the matrices. This is 4 by 2. This is 2 by 4. I have the insides agree, and I know that the resulting matrix is going to be 4 by 4. And now I can just see I'm going to take this column and swing it over, and I can see I get 3 copies of the first column of A, and I get 1 copy of the second column. So that's going to give me a 3 and a minus 1. Negative 6 plus 1 is negative 5 and 12. Then for the next column here, I'm going to end up with 2 copies of the first column, which is just 2, 0, negative 4, 8. Move that out of the way. For the next one, 1 copy of the first and negative of the second, which is going to be 1, 1, negative 3, 4. And then finally I end up with 5 copies of the last column, which is 0, negative 5, 5, 0. I recommend that you practice and that whenever we do matrix multiplication that you conceive of this as sweeping through. I'm taking the columns of B and sweeping through the columns of A to figure out how many copies of each of the columns of A I'm going to end up taking. Of course, we realize, and what I want to do is show you the other way of thinking about this. Remember, it's always rows on the left, columns on the right. And what I showed you was grabbing the columns of B and sweeping through the rows of A, which is really a linear combination of the columns of A. But we can think about this and do it in the reverse order. We could take a row of what's on the left-hand side, and we could think about sweeping through the columns of the other. So in this case, of course, the result is going to be 3 by 3. And what I'm going to do, and now you can see what's going to happen, If I take this and I flip it to the right, and I think about sweeping this through, I'm going to end up with 0 copies of the top row of B, and 1 copy of the second row of B, and 1 copy of the third row of B. And I'm going to add all of those together. So just adding the second and third rows is going to give me a -1, a 0, and a 1. All right. Let me put this back. I won't rotate the other ones. We'll just do it mentally, which is the way in which we're going to do it. I mean, you're not actually going to start copying and cutting things out. So this we can see, if I rotate this and then sweep it through the rows of B, I'm going to end up with just the top row of B, which gives me a 0, -3, 1. And then finally with this last row down here, as I go through and do the dot product with the columns, I'm going to end up with a top copy, or 1 copy of the top row and 1 copy of the bottom row, and those are going to be added together. So adding the top row and the bottom row, the first and third rows here, I end up with a 1, a -4, and a 2. So as long as I keep straight, columns on the left sweeping through, columns on the right sweeping through the rows on the left, or the rows on the left sweeping through the columns on the right, I'm going to end up in the same place, and I can pick and choose the visualization that makes things easier for me to compute and to think about. I recommend you practice with this idea. So let's talk a little bit about what we did not go through, and I'm going to leave you to read the majority of this. This is the conversation about commutativity. This is the conversation about associativity, as well as distributivity. And just understanding which of these things apply to matrix multiplication and which of them do not. Then there's a little bit of a review, thinking about the way in which Strang presents the row view and the column view of matrix multiplication. They're valuable. I think we can, using the idea I showed you, grasp both of them with a little bit of practice. Okay, moving on, we're going to talk about rank 1 matrices and the decomposition of A into a matrix product. So we're thinking about A being equal to C times R. I'm going to switch over to my yellow, right? So we have A is equal to C times R. And what this is a way of thinking about matrix multiplication. So he gives us this matrix to start. And he says down here that that matrix is actually equal to this product. Now you probably have never seen that type of product before. So he says A is equal to 132 multiplied times 1, 2, 10, 100. Let me pause and relay back for you one of the important things to understand about dot products. Okay, so we're going to hit the pause button. I'm going to shift colors, and we're going to talk about dot products for a second. So if I take two vectors, 1, -2, 1, and I dot it with 3, 1, -2, you know how to do this. This is going to be equal to 3 minus 2 minus 2, and I'm going to end up with a -1. So you know how to come up with these terms, and that's fine. What I need you to understand is there's a different way to do this called an inner product. So an inner product is if we take the transpose of the vector on the left here, and I write it as a row vector instead, and I multiply it by 3, 1, -2. So now I'm not doing a dot product. I call it an inner product, but I'm really just doing matrix vector multiplication, exactly what we just talked about, except in this case I have a 1 by 3, and here I have a 3 by 1. The insides match up, and what I'm going to be left with is a 1 by 1 matrix, which is really a scalar. And this is going to be equal to, I'm going to end up with 3 minus 2 minus 2, and that's going to be, of course, negative 1. The inner product concept is a different way to think about dot product. Anytime in general that I have v dotted with w, and I'm thinking about them both now as column vectors. Remember, our base idea for vectors is that they're column vectors. What I can do is I can write this is equal to v transpose w. It's called transpose when I take the columns and flip them over and make them rows. That's transpose. So this is a very useful way in which to think about dot products as well as computing them, of course. And this particular way of writing a dot product is also called an inner product. When you get into more advanced math courses, a little bit in this course, but more advanced math courses, and you start looking at vector spaces that are broader than just real numbers, then the whole concept of inner product becomes a very important idea. Okay, let's go back to what this thing is, which is called, and he references it here, this is called an outer product. Specifically meant to be kind of the opposite idea of an inner product. In this case, with the matrix A, I have two vectors, but instead of calculating an inner product, right, I'm calculating an outer product. And I'm going to do this in exactly the same way that we just described. I'm going to let A be equal to, and what is the size? I have 3 by 1. I have 1 by 4. The internal dimensions are 1 by 1. The outer dimension of my matrix is going to be 3 by 4. And so I'm going to think about my sweeping idea, except my column for the R matrix here just has a 1 in it. So I'm going to sweep that 1 down through the column of A, and I get one copy of the column of A, 1, 3, 2. And then my second column here is just the scalar value 2, and I'm going to sweep that through my column in A. And that's going to give me twice, or 2 copies of my column of A, and that's a 2, 6, 4. Similarly then, sweeping the 10 through, I end up with a 10, 30, 20. And then sweeping the 100 through, I get a 100, 300, 200. Which obviously leads me right back to where we started the conversation. This is a rank 1 matrix. Anytime I have a matrix built by an outer product that is simply 2 vectors, that gives me a rank 1 matrix. Really an important idea. We're going to build and use this throughout the entire course. All right, so I'm going to let you read through a little bit of this conversation about how we do the constructions of what the C matrix and the R matrix look like. And what I want to do is just ride this example that Strang provides here. So what he does to build the C matrix, and remember the C matrix contains the linearly independent columns in A. So it's going to be columns which are linearly independent in A. So in this case, the first column and the third column are linearly independent because the second column is actually just 3 times the first column. So it is the same as the first column except it's multiplied by 3. So my C matrix is made up of the first and third columns in A. Then the R matrix, which he shows here, so here's his C matrix. So the R matrix is nothing more than how do I use those columns, the linearly independent columns, to construct all the columns in A. I've admitted that some of the columns in A are linearly dependent upon earlier columns. And he does this always working from left to right. You don't have to do it that way, but in order for this decomposition to work the way that he has written it, you need to start on the left side of A and work through the columns systematically from left to right. It's not a big chore. It's the way we think about things generally anyway, but that is required for this. So let me pause and write this down. All right, so I have just a copy of what's in the text here, and I just want to explain how we're going to determine what's in R. Well, we have the linearly independent columns of A in the matrix C. And what we're going to do is we're just going to think about our sweeping through idea. So the first column of A is the same as the first column of C. So what I want is, I want one copy of the first column of C. That's going to give me the first column of A. How did I get the second column? Well, the second column in A, right here, is 3 times the first column of A, which is also the first column in C. So I want 3 copies of that first column, and I don't want any copies of the second column. So that would be 3 copies of the first column and no copies of the second column. And then finally, how did I come up with the last column here? Well, that's just my second column in C. So the third column in A is going to be the second column of C. And I'm going to grab that with a 0, 1. I'm going to bring that over, and as I sweep it through the columns of C, I'll get one copy of that second column of C, and that is the column in A. So that's the idea. Let's do one more example. So I have an example here which is similar to the one that Strang has at the bottom of this page. And remember, C is going to be built from the linearly independent columns of A, starting at the left. And of course, the first column, unless it's all zeros, is a linearly independent column from everything else because it's the first column. The second column, 4, 5, 6, is not a multiple of the first column, 4, 5, 6. So the 7, 8, 9 column, if it was linearly independent, then I would end up with C being equal to A. And if those two were equal, then R would have to be the identity matrix. I know, in fact, that the third column of A, this column right here, is linearly dependent upon the first two. And the question is how? We'll get to that in a minute. Now, for the columns of R, we're going to use this to build the columns of A out of the columns that are in C. So how do I get the first column of A? Well, that's easy. That's just the first column in C. How do I get the second column of A? Well, that's also easy. That's just the second column of C. And finally, how do I get this third column? Well, it turns out that the third column in A is actually equal to 2 copies of the second column minus the first one. So think about 2 times 6 is 12, minus 3 is 9. 2 times 5 is 10, minus 2 is 8. So the way in which I construct this last column in A is to take 2 copies of the second column and minus 1 copy of the first column. And so when I grab that negative 1, 2 and sweep it through C, I end up with exactly what I need. This is the idea. This is an example of how the concept of thinking about matrix multiplication as sweeping through can be very useful. Let's move on. We have one more topic. I'm going to leave you to read this information about the C and the R. Here he just describes how we end up finding the R matrix. He also has some interesting conversation about elimination, which is where we're going in chapter 2. Finally, what I want to discuss, so work through this example, make sure that you understand it, understand the key facts. He introduces some words here, basis and dimension. The columns in C will be a basis, and the number of columns will be the dimension of the vector space. More on that as we move forward. The last thing I want to talk about is this really somewhat bizarre but extremely important idea of how I can also do matrix multiplication using outer products. Let me write down an example. All right, so I've written down an example of matrix multiplication. This is the same one that we did previously. We're just going to attack it in a different manner. What we're going to do is, instead of thinking about doing inner products of the first column here with the first row, in order to build these values, we're going to think about doing outer products. I'm going to take the first row and the first column here. So this is contrary to our view of rows on the left and columns on the right. This is the reverse of that. It's a little bit strange, and it's an uncommon but really important idea. So he just introduces it here so that you are exposed to it and that you see it, because the resulting fact is somewhat surprising. So we take those and we build this outer product. Then we have the second column and the second row for A and B respectively, and we build the outer product here. And we're going to do that with the other two combinations. We're going to end up with an outer product here. And then finally, I guess I'll do it in yellow, we're going to end up with this outer product here. And what we're going to do is we're going to calculate, remember the outer products, each of these is going to give us a 2 by 2 matrix. So this is going to be 2 by 2 plus, and this is going to be 2 by 2 plus, etc., until this one down here, which is 2 by 2. So we're going to add together 2 by 2 matrices, and of course the result is going to be 2 by 2. Let me show you what this looks like in MATLAB. So in MATLAB, I've put the matrices in here. And what I want to do is just show you what the 2 by 2 matrices are when I do this. So I've built this vector called AB sub, the sub matrices that are going to be used to construct A times B. So looking at A and B, you can see these are the 4 sub matrices that come from these products over here. And then it turns out that the product of A times B is just adding these together. So let me come up here and sum these together. I have a command in here somewhere that will add these together. Summing them together, I end up with this matrix sum down here. And you can recall, maybe you do, maybe you don't, A times B is exactly this value here. So this is another concept of factorization or decomposition of a matrix. This idea that I can decompose it into a series of outer product matrices. But all these outer product matrices are what? They're all rank 1. So I'm going to take these rank 1 matrices, I'm going to construct them using the outer products, kind of the reverse of what we've been talking about of rows on the left and columns on the right. And then we're going to sum them together and we end up with the same value. This is a really inefficient means of calculation and we don't do this, but the idea is critically important. And when we move through the course and we start to see how we can use less and less information from matrices to come up with approximations, this idea is critically important. All right, we're going to take a look at the questions here. And let me pull those up. So these are the questions for today's lesson. Go ahead and take a look through those, and remember that we will discuss those in class, so please be prepared to answer. Thanks very much.